Hello there. Thanks for watching and I appreciate you. This is a video in a series of videos showing you how to make a custom character controller that uses rigid body physics, Cinemachine cameras, Unity's new input system, and custom player gravity. In the last video, we gave our player the ability to manipulate other rigid bodies by repelling or attracting them, added an item counter for the number of rigid bodies we collected, and introduced a very basic game manager which locks and hides our mouse cursor. In this video, we're going to increase our number of playable characters and make it possible to switch between them. We're going to build on our game manager, and finally we're going to learn a little bit about Unity's update and fixed update functions. Before diving in, just a reminder, this project is exactly how we left it in the last video of this series, and just like in the last couple of videos, I'm going to treat this video as being a little more advanced. That means I'm going to skip over the simpler things and assume that at this point you've been following along the series and are familiar with Unity and my methods. If you have not watched this series yet, then I would strongly encourage you to do so. As always, if you have any questions, please feel free to ask them in the comments below. I do try to reply to everyone that comments. And finally, we also now have a community Discord server. The link to join the Discord server is in the video description below. Alright, let's get started. First, a quick side note from the last video. I forgot to mention that the positioning of the text that we did directly relates to the resolution of the game. The simple solution here is to simply make sure that your game panel is set to full HD. With that mentioned, let's start as we usually do by setting up our new input. So in our project panel, let's navigate to our input actions and open that up. We're going to add a new action. We're going to call it switch character. And for the action type, we want a button, which is what the default is. We're going to add another binding. And for our first binding, we're going to do our gamepad, button east. And for our second binding, we're going to set it to our tab key. Don't forget to save the asset, and then we can close the window. Next, let's add it to our input handler. So let's open up our humanoid land input script. In our humanoid land input script, I'm going to make a few changes, and then we will review them. Okay, so all we did was we added this public boolean called switch character was press this frame. We can get it from anywhere, but we're only going to set it locally, and by default its value is false. If we scroll down to our update function, in our update function we're checking to see if our switch character button was pressed this frame, and whatever was going on with this frame, we're going to store that in our switch character was pressed this frame variable. Okay, we're done with our input already. Let's jump back to Unity. And in Unity, we're now going to create our second playable character. In the hierarchy panel, let's drop down the player game object, humanoid. We're going to right click and duplicate our red game object. And we're going to rename it and call it blue. Next, let's drop down our new blue game object. And let's select our player game object, which is our cylinder representing our player. And in our inspector panel, under the capsule mesh filter, let's go ahead and let's click the bullet here. And let's change it to a cylinder. And under our mesh render, let's click the bullet for our red, and let's change it to blue. Finally, let's move our blue characters somewhere else so that they're not right on top of each other. Let's simply just change our player's position in the inspector panel, and we're going to change his X to, say, -35 should be good. Okay, with that done, let's go back down to our project panel and open up our game manager script, where I am going to once again cut corners and copy and paste the script. Okay, now that our game manager is magically populated, we can go over each line and see what exactly it does. Right off the bat, we're linking in our input, our camera controller, as well as both of our humanoid land controllers attached to both our red and our blue players. And then we're declaring a few variables. The first one is called is vSync enabled. It's a boolean and we're setting it to false. Next one is called target frame rate. It's an integer and we're setting it to 120. And the last one is called target physics rate. It is a float and we're setting it to 60. Our first function is the awake function, and in our awake function, we're setting our vSync count, our target frame rate, our fixed delta time, and our maximum delta time. We'll come back in a bit, and we'll talk about these a lot more later on when we start talking about update versus fixed update. For now, let's scroll down further and look at our start function. In our start function, we have the exact same two lines that we have here from our last video still, and all they're doing is they're locking our cursor to the middle of the screen and also hiding our cursor. Moving on, let's scroll down a little bit further to our update function. In our update function, we're checking to see if our switch character button was pressed this frame. Then we're going to take our red controller and our blue controller and we're going to swap their current values. I'm going to take a second real quick and reformat these lines so that we can see them all within our window. Okay, now we can see all of our code within the viewport. All we're doing is we're accessing our camera controller, and from each of our 3 cameras, we're getting our Cinemachine virtual camera component, and we're setting the follow and the look at for each. Depending on which one is enabled, we're also going to set this to the follow and the look at of our cameras, and that's going to handle our camera switching. Finally, down at the bottom, we just have some last little switching around to do, and all we're doing is we're getting the component in our children called manipulator, and we're switching whether it's enabled or not based upon whether it's already enabled or not. So in summary, all we're doing, if the switch character button was pressed this frame, then we're going to switch around whether our input is enabled or not, which player our cameras are going to follow, and also which manipulator is enabled or not. So obviously we just have two characters. This is pretty simple for now. I just wanted to show you what all was involved. Now before we can do a playtest, we gotta jump back into Unity and finish setting up the script. So let's go ahead and do that now. In our hierarchy panel, let's select our game manager. And under the game manager script, we just need to set our input. Click the bullet for each. So we just set our input to our input handler, our camera controller obviously to our camera controller, our red controller to our red humanoid land controller, and our blue controller to our blue humanoid land controller. And finally, in our hierarchy panel, we need to once again select our blue player game object. And in the inspector panel, we need to disable our humanoid land controller script. As well as back in our hierarchy panel, we need to drop down our camera follow and select our manipulator and also disable our manipulator script. With that done, we're now ready to jump into a playtest and see it all work. And here we are in a playtest. Let's go ahead and let's get some blocks collected real quick. Alright, you can see our other player over here. And if I press the switch character button, you'll see that we now control this player, or character, or whatever you want to call him. And also, if I were to collect blocks with this character, you can see it affects our same counter because we made that public. But you can see that everything works properly. This character is no longer moving. Our cameras are now all switched. And you can see that we do indeed hide our player when we go into first person. We switch back out to third person orbit. And everything works as intended. Now there is one little problem with this. For example, if I were to use my attractor on this player, you can see that I pull him in and then we count him as a box that was collected and then he disappears. And now if I press the button to switch characters, we will be greeted with an error. The reason for the error is pretty obvious. It's because our player that we're trying to switch to no longer exists. But if we go to our console, that will confirm it with a missing reference exception. The object of type humanoid land controller has been destroyed. In the previous video, we already implemented what we needed to resolve this. We just need to finish implementing it now. But let's go take a look at the script real quick and we will talk about what exactly it does. So here we are in our manipulator script, and if we scroll down to our onTriggerState function, here we're checking to see if the object that we're trying to attract is not a player, so it's checking the tag on the object for the word player. Then we can set to use gravity back to true. Otherwise, we do not want to add Unity's gravity to our player because we are using our own gravity. Likewise, if we scroll down to our onCollisionEnter function, we are once again checking to see if not collision.GameObject.compareTag is player, then we'll destroy it, and we will count. So we have the check already here. All we need to do is go into Unity and add the player tag to our players. So let's go ahead and let's do that now. Back in Unity, in the hierarchy panel, let's select our red player. And in our inspector panel at the very top, we have our tag is currently untagged. Let's go ahead and select the player tag. If you do not have a player tag, you can go ahead and create a player tag, but we already have one, so let's select it. And then let's do the same thing to our blue player object. And now if we jump back into a playtest, we can go ahead and try this again, and we will not be able to destroy our other player. Much better. One other thing worth noting is that since we disabled the entire controller script on our player, we've also disabled our custom gravity. That's obviously a little bit of a problem, but not one we're going to solve in this series. But let's go ahead and stop this, and let's talk about update versus fixed update. Alright, let's talk about Unity's update and fixed update functions. We're not going to go into too much detail here. I really want to do a deep dive into it in a video dedicated to just this topic. But in this video, we'll get off to a great start about understanding the two, their key differences, and why they're important. By the end of this, you will know when it's appropriate to use each of the aforementioned functions, which is quite a feat considering this is a topic that has a ton of confusion surrounding it. Now, as a general disclaimer, I'm no game developer historian, but I'll share what I know and what I found to be most helpful. To start, if you do a Google search for Free the Physics, the first result will likely be a page called Fix Your Time Step by Glenn Fiedler on GafferOnGames.com. It's a post that dates back to 2004, but even today it's still a very worthwhile read. It's a 10-minute-ish read, and throughout Glenn details a lot of the pros, cons, and solutions to quote-unquote freeing the physics. You'll also see where he talks a lot about running the physics at 50 frames per second while display frame rate is running at 60 frames per second. If that doesn't sound familiar, Unity by default runs its physics/FixedUpdate quote-unquote loop at 50 frames per second. A lot of modern day game-related physics simulations, I guess you could say, revolve around this Fix Your Time Step article. Hopefully at this point I've perked your interest a little by now, and so for your convenience I'll put a link to this article in the video description. I strongly suggest that you pause this video right now and go read it. Don't worry, this video will not self-destruct and will wait patiently for you to return. Alright, if you haven't already, hopefully you have read that article now, and you should kind of understand where Unity gets a lot of its keywords from. Now let's take all this information we've gathered so far and put together in something that's hopefully a little easier to absorb. So here I'm going to lay out. On the left we have update, on the right we have fixed update. Let's keep in mind that these are two different loops entirely and that they operate independently from each other. The update function is the game's main game loop. Every game and program that runs is just a loop that keeps looping until you close the game or program. In Unity, this main game loop happens within the update function. It's primarily responsible for all game logic and rendering, meaning that it handles things like player input, game logic, and rendering each pixel that is ultimately displayed on your screen. It can be allowed to run as fast as the host computer can process it, or it can be attempted to lock it to a fixed rate. However, it's important to note that neither of these allow for perfectly consistent frame rates. I think now is a good time to address one of the most common mistakes I see within the update function, and that is the overuse of multiplying pretty much everything and anything by Time.deltaTime. Say, for example, one frame renders at 100 frames per second, and the frame right after that renders at only 50 frames per second. If we move an object in the game at a rate of 1 meter per second, then our object will not move at a consistent speed. If we're expecting the game to run at 100 frames per second, then we're expecting the object to move 0.01 meters, aka 1/100th of a meter, or 1 centimeter every frame. But if a few frames per second are running at only 50 frames per second, then our object will only move 0.005 meters, aka 5/1000ths of a meter, or 5 millimeters for each of those frames. This inconsistent frame rate will cause an inconsistent rate of travel, which is completely quote-unquote frame rate dependent. To solve this, we can attempt to measure the time in between frames and then multiply the amount of movement by that. Fortunately, Unity does this for us and reports the amount of time between frames as Time.deltaTime. On a side note, it's nearly impossible to get 100% accurate time in between frames due to the nature of the beast, but just keep that in the back of your mind that this value in most use cases is quote-unquote close enough. Anyway, now that we have this amount of time in between frames, we can multiply our desired amount of movement by our Time.deltaTime to create a frame rate independent value. So going back to our example, if our desired amount of movement is 1 meter per second, then in one frame that rendered at a rate of 100 frames per second, the Time.deltaTime would be 0.01 seconds. And if we now multiply that Time.deltaTime by our desired amount of movement, which in this case is 1 meter per second, the resulting value will also be 0.01 meters. However, for frames that take longer, using our example again, if a frame took twice as long to display by only running at 50 frames per second instead of 100, its Time.deltaTime would be 0.02 seconds. And if we now multiply that by our desired rate of movement, the resulting value will also be 0.02 meters, which is exactly what we need to keep moving at a constant rate of speed. Because again, since the time to render was twice as long, our amount of movement is also going to be twice as much. Hopefully that brought some clarity as to proper usage of Time.deltaTime, and now we can move on to fixed update. So the fixed update loop runs separately from the update or main game loop as it attempts to run as consistently as possible at a fixed rate. In Unity, this fixed rate can be referenced with Time.fixedDeltaTime. We're not going to go too much into Unity specific time and frame rate management and how Unity handles a frame rate that is less than ideal. I'm going to spare you that headache for now, and later I'll hopefully be able to put together a far more in-depth video. If you did read the Fix Your Time Step article that I mentioned earlier, you're already at least a little aware of these headaches and should be able to start connecting the dots yourself. Again, if you haven't read that article, I suggest you read it. Now let's go back to our game manager and look at those values that we skipped over initially. In the awake function, we're setting some values, and what we're setting here I've configured just for testing purposes on a PC. These are by no means values that I would suggest using. Each game, especially depending upon the platform that is being developed for, will require different values and options. Some are enforced dependent on the platform, especially with mobile applications for example, and some you may even want to leave up to the player to select. But I digress. Back to the awake function, our game manager script. In the first line, we have QualitySettings.vSyncCount equals is vSync enabled. If it is enabled, then we're setting it to 1. Otherwise, by default in Unity, this is set to 0, which means that it is disabled. So in this line, we're setting the vSync, aka the vertical sync. If you're not familiar with what vSync is, then its primary purpose is to help prevent screen tearing by basically limiting the frame rate to whatever the display's fresh rate is. For example, if you have a 60Hz monitor, then your FPS will be capped at 60 frames per second, 144Hz monitor, 144 frames per second, so forth and so on. QualitySettings.vSyncCount has 5 different possible values starting from 0 and going up to 4. As I just mentioned, 0 is the default value and means that vSync is disabled, while 1 enables it. Setting it to 2 means that vSync is enabled and that the frame rate will be half of the monitor's refresh rate, while 3 will be a third of the monitor's refresh rate, and 4 will be a quarter. To give a basic example, the usefulness of these extra settings is meant mostly for mobile games, as it can be very useful for conserving battery life. Anyway, I don't want to get too much into other platforms and all of that in this video. Let's move on while keeping our focus on PCs. In the next line, we have Application.targetFrameRate equals our target frame rate variable. As is being suggested by the name, we're setting our ideal frame rate here, and we're setting it to 120 frames per second. Note how Unity has chosen to call it a target frame rate. As I mentioned earlier, the frame rate can never be assumed to be exact, hence here is referenced as being a target. In the next line, we're setting Time.fixedDeltaTime to equal 1.0 divided by our target physics rate variable. We currently have our target physics rate variable set to 60, which means 60 frames per second. So this is a bit of math, just gets us amount of time equal to that 60 FPS, which means that each physics update is going to happen every 0.016 to infinity seconds. Of course, this doesn't actually go to infinity, and Unity does eventually automatically round it up to a 7, as seen on your screen now. Once again, as was mentioned in the Fix Your Time Step article, there are a few possible problems when you free the physics. One of the ways Unity has decided to deal with some of these problems is by setting a maximum delta time. If a frame takes a long time to render and display for some reason, then the reported Time.delta-time will be limited to the value of Time.maximumDeltaTime. On your screen now is a time flow chart directly from Unity documentation showing you exactly how time flows in Unity. You can find a link to this time flow chart in the description below. To give an example of this happening, say the game for whatever reason locks up on a single frame for 5 seconds, but the maximum delta time is set to 1 second. In game time, it would have been as if only 1 second had elapsed despite it being 5 seconds in real time. This means that the system would only need to compute 1 second worth of physics rather than all 5 seconds, effectively reducing the computational load by roughly 80%. This addresses the issue of a system falling behind and never being able to catch up again. Now going back to our game manager script, here we are setting our Time.maximumDeltaTime to equal our Time.fixedDeltaTime multiplied by 1.25, which effectively equates to 48 frames per second. This means that our Time.deltaTime will never be reported as being below 48 frames per second. If you're interested, you can see on your screen now some math showing what exactly these values will be. You can go ahead and pause the video now and review those if you like. Otherwise, that wraps up what I was wanting to talk about with our game manager. If you have any questions, please stop by our community Discord server to ask there. Myself or someone else there will be happy to help. Link to join the Discord server is in the description below. Next, let's backtrack a little bit by going way back to when we first set up Cinemachine in our project. If you've been following along with the series, you'll remember where we set our camera's Cinemachine brain to update on FixedUpdate instead of the default LateUpdate event. For your reference, here's that setting now on your screen. Now you might be wondering what is LateUpdate and why is it the default option in Cinemachine. LateUpdate happens within the same game logic section of the model behavior flowchart as seen on your screen now. If you're interested in seeing the full flowchart, I'll put the link in the description below. LateUpdate is very similar to update, except it's the last thing that happens before the actual rendering of a frame happens. Basically, our update event happens, we do all of our waiting, coroutines, animations, and then finally we're at LateUpdate. Moving the camera in LateUpdate and all other objects in update ensures that all movement has happened before we attempt to move the camera. With that explained, we changed the setting to fix the problem of our game showing some apparent stuttering. Since this is a physics-based character controller, the character's movement will be updated along with the FixedUpdate event, which means that the camera's movement should also be updated then too. If the camera's movement is not updated then the odds of FixedUpdate updating at the exact same time as LateUpdate are not very good at all and will result in the sort of camera stuttering effect. It might also be worth mentioning now that the opposite scenario is also true. If any movement that is now done within the update or LateUpdate events may also display with sort of stuttering if the camera is set to update on FixedUpdate. If you have a project or game that utilizes movement within both update and FixedUpdate, then a solution you may need to use is to use 2 cameras, each camera using a different update method and each only showing those objects that move via that method. Moving on, there's one other thing I think we should at last make mention of is the fact that we're not handling input correctly. and we've left room for the possibility that input could be missed or even incorrectly applied. Once again, on your screen now is the flowchart for Unity's default monobehavior class. If you missed it the first time, the link for this is in the description. As before, you can see the game logic loop containing the update and late update events. If we look just above that loop, we'll find where the input events are processed within the main loop of our game, which means that our input is processed once every frame just before the update event is called. Consequently, it is then made kind of obvious that input should generally be handled within the update function. However, currently we're handling the vast majority of our input within the FixedUpdate function. As you should know by now, update and FixedUpdate are, for the most part, independent from each other in their timing and execution, which means that input could get missed or misinterpreted if we're handling it only in FixedUpdate. To solve this is pretty simple. What we should be doing is checking for input in the update function and marking it only as having been handled in the FixedUpdate function. I don't want to go any more into this in this video, but it's just something to be aware of. I'm sure I will address this officially sooner rather than later, but just did not want to add this additional complexity into this series. With all that said, that's going to be it for this video. I hope you found it helpful. Feel free to ask if you have any questions. I also want to take a moment to thank you for watching. These videos take quite a bit of effort to put together, so if you enjoyed, help me help you by liking this video and subscribing to the channel. Additionally, we have a community Discord. If you'd like to join us on Discord, the link is in the description below. The next video is going to be the final video in this series, so you won't want to miss that one. Make sure you're subscribed and tick the bell for notifications so you don't miss it. Thanks again. I'll see you in the next one. If you're feeling generous, leave a comment down below. I want to read what you're thinking. Let me know if you have any questions or recommendations. I'd also appreciate it very much if you liked the video. And if you're feeling extra generous, it'd blow my mind if you subscribe to the channel. Being new to this and putting these videos together takes a lot of time and effort. Thank you for any and all participation and support. I look forward to continuing this in the next one. See ya.